Next problem I would like to look at problem number 16. That one's in 5 brackets. Okay. So to get 16, I really would like to look at what a cosine looks like. And I have a cosine right here. So a cosine of x would look like that. Well, let's see how this works. This is going to be x squared times 1 minus hopefully we're getting the hang of this. So basically, this is the only varying value. Basically, if I'm multiplying this by x squared, I would just multiply this by x squared. And this would be, let's see, what's taking the place of x? It's x squared. So altogether, I would say that is x squared minus, this is x to the 4th, that's x to the 6th over 2 factorial plus, this is x to the 8th, that's x to the 10 over 4 factorial plus, this is going to be x to the 4n plus 2 from that, divided by 2n factorial. And that would be, again, I don't know why I'm pushing this so much, that would be the series n equals 0 to infinity, negative 1 to the n. This is going to be x to the 4n plus 2 over 2n factorial. If I can make that x to the n, I should, in this case, it doesn't work that way. Now here, oh, with all the excitement, I forgot to copy directions. So this is more what directions on the exam would look like. So if I say find the power series, you must start from scratch like section 10.8. If I say use power series, you could use the table. So I'll remind you of that before we take a test. Once we vote for a test date, I'm going to remind you of that one more time. I'm going to do one more example and show you where's this used for. Aren't you anxious to know? So now I'd like to look at another problem, and let me look at 20. Multiplying sine times sine is hectic. And can we see why? Multiplying this quantity by itself, foiling and combining to figure out a formula is a lot more challenging than you think. Luckily, we know about identities. We just learned about integration. We know this is 1 minus the cosine of 2x divided by 2. So we would say this is 1/2 minus 1/2 the cosine of 2x, and that would be 1/2 minus 1/2 times, and what's cosine? Well, we just did cosine on the previous problem. It's right there. And what are we going to replace x with? 2x. And what would that be? That would be 1 minus 2x squared over 2 factorial plus 2x to the fourth over 4 factorial, which reminds me, so that we haven't be on top of each other, that's a mistake or something like that, there it is, plus a negative 1 to the n, 2x to the 2n over n factorial, and what would that be? Oh, it doesn't end. So that would be 1/2 minus 1/2 times the series n equals 0 to infinity, negative 1 to the n, 2x to the 2n over 2n factorial. Now, something happens. This is 1/2 minus 1/2 plus this is going to be 2 squared x squared over 2 times 2 factorial. This is going to be 2 to the 4th x to the 4th over 2 4 factorial minus, when you distribute it into that, that's going to be negative 1 to the n. And this is really where you want to do the work, right? Because that's what this is. And what would that be? Those cancel out. So instead of getting there first, look at this, say, okay, the one term cancels out, and this cancels one of those. That's 2 over 2 factorial x squared, plus this cancels one of those. That's 2 cubed over 4 factorial x to the 4th, plus negative 1, it should be minus, should have. Negative 1 to the n. This is going to be 2 to the n minus 1, combining those two, over n factorial x to the 2n. That would be the series n equal to infinity. So I know this is really what this part is. That's why I didn't bother writing it up there. You don't have to reinvent the wheel twice. You know exactly how this works. The catch is, do you see that this power series right here starts at 0? Do you see we lost one of these terms? We no longer start at 0, now we start at 1, and that's pretty much what it is. Sometimes that happens. You lose a term, maybe 2 terms, depending on the problem. Now, the homework in this section, I just want to point out what this is, and we'll give you the homework. Well, no, let me give you the homework now. This is section 10.10, 10.9 on page 647. And you're going to do numbers 1 through 25 of the upper part. Now, I want to show you something really quick on page 645. This is something that we played with in math. It used to be 201, now probably it's 2010. Let me show you this graph and elaborate on that a bit. Did you ever hear somebody saying you could describe any function by a polynomial if you take the degree to be high enough? I don't know if you heard that before. I heard that back in the days, and I didn't know what it meant. They said you could describe any function you want. They were talking about Taylor. I don't know if they were talking about Taylor, but you know. I'm looking at this graph. The blue curve. Do you see that? That is the graph of y equal the sine of x. If I take the sine of x that I did in the previous section, do you remember the last portion? I'm going to show you really quick. Do you remember when we took those and we started talking about polynomial representation of those. So remember the sign when we said P of 0 is 0, P of 1 is x, right? There is no P2 really because it zeroes out every other term, so it's really x to the 1, x cubed, and so on and so forth. Look at this graph. Isn't y equal x right there? So if you stay around 0, this line is a good approximation of this curve, but don't go far enough. When you go to 1, then we're going to really be looking at 1 minus x cubed over a number. Do you see that this describes this a bit further to 2? If you go further than that, then we're going to take and do you see to around x equals 3? This curve describes that very well. And if we keep this trend going, that is, if we look at P sub 7, do you see 7 is very close to this, further than 3? And if you go far enough, then we're going to use, oh, that's the same color, you can see it. We're going to use the 9th degree polynomial, and that would become more accurate, closer to the curve. And notice how each power extends that even further. Every power really is mapping what the sign look like to further and further depending on how far you want it. Meaning, let me just elaborate really quick. If I take, for example, I'm going to use yellow, it's hard to see, that's intentional. If I want to really map sine of x, let's say to x equals 7, do you see that's what the 17th degree polynomial look like, and it's very close to sine. And what's the benefit out of that? Once you do programming, you're going to figure out sine is an irrational number. Polynomials are really easier to use. If I want to know what the sine of 0.1, that's 1 over 10. I'm not saying a 13th degree polynomial is really easy to use, but it's easier to take 1 over 10 to the 13 and figure that out than to try and figure out what this irrational number is. And once you do some programming, you will figure out how many iterations it takes to find an irrational number versus just using a 6th or a 7th or a 5th degree polynomial. Iterations vary drastically. Alright, so that's the end of 10.9. If it wasn't online, I would have probably did more, but we are limited.